Today we just want to focus on this idea of using vectors to solve geometry problems. So a couple of things to keep in mind. Use one of the vertices, not always, this is just a guide. If you choose one of the vertices and make that the origin, it just makes it easier for referring your vectors, so you've got some point. Keep in mind, sum or differences of vectors, we can create a triangle with three vectors. Parallel vectors are multiples of each other, so these are all sorts of things to keep in mind. If we need to find an angle in our shape, we can do that using the dot product. That's very useful for proving things are perpendicular, because we can show the dot product's equal to 0. And we can always work out the position vector, head minus tail. Head minus tail. Okay, so we're going to prove that the diagonals of a rhombus are indeed perpendicular. So OABC is a rhombus. So conveniently, I've made one of my vertices O representing the origin, if you like. So OA, I will then just call the vector A, and OC I'll just call the vector C. Now, we want the diagonals. So one diagonal there, well, that will be A plus C, the addition of the two vectors. And the other diagonal, it doesn't matter whether I can call it A minus C or C minus A, it all just comes down to the direction I make that vector. So I've made it C minus A. Okay, we want to prove that those two vectors are perpendicular, basically. So if I look at the dot product of A plus C and C minus A, which essentially is difference of two squares. So I get C dot C minus A dot A, magnitude of C squared minus the magnitude of A squared. But remember, this shape is a rhombus. So therefore, the magnitude of the vector A must equal the magnitude of the vector C. Because sides in a rhombus, we know, are equal. So therefore, our dot product equals 0. Thus, those two vectors must be perpendicular. Mind you, now you'll notice I'm not calling them a vector, I'm just calling them the interval OB and AC representing the diagonals in a rhombus. So there's a neat little proof. What about Pythagoras' theorem then? Yes, I mean there's many, many different ways of proving Pythagoras' theorem. Here's one using vectors. So OAB we know is a right angled triangle. Again, I'll make one of the vertices, and I've made it the one where the right angle is, the origin, so I'll call that O. And so OA, I'll call the vector A, OB, I'll call the vector B. So we basically want to prove a Pythagoras' theorem, which of course says correct. Although in this case it won't be C squared, because that vector, again the way I've written it, it'll be B minus A. Well, let's have a look. OA squared plus OB squared would be the magnitude of A squared plus the magnitude of B squared. AB squared will be the magnitude of B minus A squared. Well, that would be the dot product of B minus A dot B minus A. Well, if I expand that out, I get B dot B minus 2A dot B plus A dot A. I can get rid of the A dot B, can't I? Because we know that A dot B is going to equal 0, and B dot B is the magnitude of B squared. A dot A is the magnitude of A squared. So yes, it does equal OA squared plus OB squared, thus proving Pythagoras' theorem. Now, let's have a look at this little one. Is that a little bit more interesting? ABCD is a quadrilateral. PQ and RS are midpoints of AC, BD, AD and BC. What type of quadrilateral will we get when we join up P, R, Q and S? Okay. Well, I'm going to take A to be the origin. If they'd labelled one O, I probably would have taken that one, but they haven't. So I'm going to say, well, look, let A be the origin. Then that way I can call AB, I'm just going to call the vector U. AC, I'm going to call the vector V. And AD, I'm going to call the vector W. I mean, I suppose I could have called them B, C and D, but hey, no need to. I can call them whatever I like. So P is half of AC. Remember, it was the midpoint. So I know vector-wise, AP will be a half of V. And I can do a similar thing over there. Q, well, BD we didn't name anywhere, but we know it's going to be head minus tail. So it's half of BD, so it'll be a half of W minus U. And R, Sorry, just you can't help yourself really, can you? Now AD we've named as W, so we know R is half of the vector W. Now, any other points we don't know yet? S would be a half of BC. We haven't given a name to BC, would be V minus U. Okay.
So, how do you know you only have to define 3 of the vectors? You know what I'm saying?
Well, because I've chosen A to be the origin, and there's only 3 vectors coming out from that.
And the rest are just...
The rest then I'll make up, if I can, from those ones that I've named. Yeah. Okay, so we're interested in looking at the sides of this quadrilateral. So PR is one of the sides. So now I can substitute in and work out what it is. Head minus tail. P, we worked out R, so we get a half of V minus U. SQ is its opposite side. So let's see, and we also get a half of V minus U. So what is that telling us? They're parallel, they're certainly parallel, but they're equal as well. So we're talking about a quadrilateral where opposite sides are equal and parallel. Got to be a parallelogram. 8D.